Hello students, welcome back to the 8th video of this playlist. In this video, we will be solving question number 8 from one of the most recent past paper of further pure mathematics, which is the May 2024 F1 paper. So let's get started with question number 8 of the paper. So here in question number 8, the question is asking to prove by induction that for n element positive integers, f of n equals to 7 to the power n minus 1 plus 8 to the power 2n plus 1 is divisible by 57. This is proved by induction. So the first step of proof by induction is that we have to show that the given statement is true for n equals to 1. So let's consider when n equals to 1, f of 1 equals to 7 to the power 1 minus 1 plus 8 to the power 2n plus 1. That is 2 times 1 plus 1, which is 2 plus 1. Okay, so that would give you 7 to the power 0. It is basically 1 plus 8 cube. So 1 plus 8 cube, it is basically 8 cube is 512 plus 1, it is 513. So basically 513 can be written as 57 times 9. So f of n is divisible by 57 when n equals to 1, right? Hence the statement is true, is true for n equals to 1. Okay, this is the first step done. Second step is basically the induction step, inductive step or induction step, whatever you say. So in induction step, we have to show that the given statement or the given statement is true for n equals to k and n equals to k plus 1. So basically we will not directly we can't directly show that the given statement is true for n equals to k and the given statement is true for n equals to k plus 1. Basically we have to do some induction here. So for induction, at first we will get the equation for n equals to k, the equation of f of k at first. So when n equals to k, you will get f of k equals to the equation for f of k would be 7 to the power k minus 1, okay, and then plus 8 to the power 2k plus 1. This is the equation of f of k when n equals to k. Okay, now get the equation for n equals to k plus 1. Okay, so basically we can't show for n equals to k and n equals to k plus 1 directly. Okay, we have to do some induction here. Okay, so before doing the induction, let's get the equation for k and k plus 1. So that would give you k plus 1 minus 1 plus 8 to the power 7 to the power n minus 1. N is k plus 1, so k plus 1 minus 1, that's fine. 8 to the power 2 n plus 1. So 8 to the power 2 times k plus 1 plus 1. Okay, so the equation for f of k plus 1, it is basically 7 to the power k plus 8 to the power twice of k plus 3. Okay, now how can we do the induction step? Look, we will subtract f of k from f of k plus 1. Okay, we will subtract f of k from f of k plus 1. So if you do so, what you will get, f of k plus 1, it is 7 to the power k plus 8 to the power twice of k plus 3. This is k plus 1 minus f of k. F of k is 7 to the power k minus 1 minus 8 to the power 2k plus 1. Okay, now we got 7 to the power k, and we got here 7 to the power k minus 1. Okay, so 7 to the power k can be written as 7 to the power k plus 1 minus 1, or we can do the reverse, the opposite, k minus 1 plus 1. Why I'm doing this? To make it similar to this one. Okay, and 8 to the power 2k plus 3 there, so we can write 8 to the power 2k plus 3 like as this. Look, 8 to the power 2k plus 3, it can be written as 8 to the power 2 plus 2k plus 1. So it got similar to this one, isn't it? That's why I'm doing this. Okay, so 8 to the power 2k plus 1. Like, you have to understand like why I'm doing this, why I have written 7 to the power k like 7 to the power k minus 1 plus 1. There is definitely a reason for doing this. You have to understand the reason. Okay, so this is the equation for f of k plus 1 minus f of k. Okay, so f of k plus 1 minus f of k, it would be 7 to the power k minus 1 times 7. So we can write 7 times 7 to the power k minus 1. Okay, minus 7 to the power k minus 1. And here we can write 8 squared times 8 to the power 2k plus 1. Okay, and then minus 8 to the power 2k plus 1. Okay, so f of k plus 1 minus f of k, it can be written as, from 7 we are subtracting 1, so that would be 6 times 7 to the power k minus 1, and 8 squared is basically 64, so 64 minus 8, it is basically 63 times 8 to the power 2k plus 1. Okay. Okay, now we got the equation for subtraction of f of, we got the equation for the difference of f of k plus 1 and f of k. So basically we have to represent this subtraction in terms of f of k. So why do we need to do this? Because this is the induction process. In induction process, you can't show anything directly. You have to represent it in terms of one to another. Okay, so in induction step, basically we have to prove that the given statement is true for n equals to k and n equals to k plus 1. That's why we can't do this directly, and that's why we have to do some induction. Okay, so as for induction step, we have to represent this difference between f of k plus 1 and f of k. We have to represent it in terms of f of k. So if you see the equation for f of k, if you see the equation of f of k, it is basically 7 to the power k minus 1 plus 8 to the power 2k plus 1. Can you make some relationship with the equation for f of k with the equation of difference? Definitely there is. Look, we got 7 to the power k minus 1, we have 7 to the power k minus 1 here, right? And again, we need 8 to the power 2k plus 1, we have 8 to the power 2k plus 1 here. Okay, so what we can do here is that we need to show that we have to represent it in terms of f of k. Okay, let's write the equation for f of k. It is basically 7 to the power k minus 1 plus 8 to the power 2k plus 1. Okay, so if we have 7 to the power k minus 1 plus 8 to the power 2k plus 1, okay, we can make it multiple of something. Okay, look, if we take 6, if we take 6 times of that, 6 times of 7 times 7 to the power k minus 1, plus 6 times of 8 to the power 2k plus 1. So it is, there are 63 8 to the power 2k plus 1, but here we have 6 times 8 to the power 2k plus 1. So remaining is how much? There are remaining 57 8 to the power 2k plus 1. Okay, so the main concept is that we are trying to represent the difference between f of k plus 1 and f of k in terms of f of k. So to do that, we have represented the equation for f of k here, and then we made it multiplied with 6, and then we got 57 there. So 6, we got 6 times, so f of k plus 1, f of k plus 1 minus f of k can be represented as 6 times of f of k. We can write this as f of k plus 1 minus f of k. We can write it as 6 times of f of k plus 57 times 8 to the power 2k plus 1, right? So look, if you take f of k plus, if you make f of k plus 1 the subject, you will get 7 times f of k plus 57 times 8 to the power twice of k plus 1. Okay, so we got, there was 6 f of k was there. Okay, now we got 7 times f of k plus 57. Okay, so 7 times f of k plus 57 times 8 to the power 2k plus 1. That's what we got the equation for f of k plus 1. Okay, so what you can deduce from this equation for f of k plus 1? Look, 7 times, this is 7 multiple of f of k plus 57 times 8 to the power 2k plus 1. So definitely 57 times 8 to the power 2k plus 1, it is a multiple of 57. And if f of k is a multiple of 57, then 7 times a multiple of 57 is definitely a multiple of 57. So multiple of 57 plus multiple of 57. So definitely f of k plus 1 will be a multiple of 57 if f of k is a multiple of 57. That's what we have represented here. So basically, in the inductive step, the main focus you should have is that you have to represent the difference of f of k plus 1 and f of k. You have to represent this difference in terms of f of k. Okay, and that's what we did here exactly. And we could show that here, if f of k is multiple of 57, if f of k is divisible by 57, then definitely f of k plus 1 will also be divisible by 57. Okay, so f of k plus 1 is divisible by 57 if f of k is divisible by 57. Okay, therefore it has been showed that that f of n is divisible when n equals to 1, and it is divisible when n equals to k plus 1, when n equals to k plus 1, if f of n is divisible, okay, and it is divisible by 57. We have to mention if it is divisible by 57 when n equals to k plus 1, if f of n is divisible by 57 when n equals to k. Okay, hence proven that f of n is divisible by 57 when by 57 for all positive integers n. Okay, for n element positive integers. That's it, and that's the answer for part 8. Fine.